Hello everyone, my name is Salesh Trivedi. I am the product manager for Oracle Database Sharding, which enables hyperscale globally distributed databases. We'll have a quick overview of sharding, then we will look at how it actually works under the hood, and we will discuss some of the new features we introduced in Database 21C. So what is database sharding? Sharding has been the dominant approach for which has been used to scale internet applications. Effectively, it is horizontal partitioning of data across independent machines. It uses a shared nothing architecture and it enables massively parallel processing. So in this picture, I'm showing that we have three machines, server 1, server 2 and server 3. Let's assume each of these servers have an instance of Oracle database. We call it shard. So server 1 has shard 1, server 2 has shard 2, server 3 has shard 3. And in this database, let's assume we had a table called table 1. This obviously you can have more than one tables, but for the sake of discussion, let's assume we have a table called table 1. And this table is spread across all of these three shards. If this table had 300 rows, then what we do is we put row number 1 to 100 say on machine 1, 101 to 200 on machine 2, and 201 to 300 on machine 3. So effectively there is a single logical database which has a single table, but we have partitioned the data in this database and in this specific table across all of these three machines. So each of the shard holds a subset of data, and there is no single point of failure in this architecture. So the shards are replicated for high availability, and we'll take a look later in the session. It's a shared nothing architecture, which means that the shards don't require any specialized hardware or software. For example, we don't need a specialized network attached storage or a SAN storage. No need for any specialized network cards, NICs, host bus adapters, none of that is needed. Nor do we need any specialized software like clustering software. So these shards are independent. At the runtime, they don't communicate with each other. Actually, they don't even know that these shards don't even know that there are other shards in the system. So all of these shards are completely independent and they use a shared nothing architecture. Now when the application connects to the shards, from an application point of view, from an operational point of view, it's a single logical database. So when the application connects to this shard, we have enhanced our client-side drivers like our JDBC driver, Universal Connection Pool, .NET driver, C driver, C++, Python, Go. All of those drivers understand sharding. So from an application point of view, it's a single logical database, and our drivers connect the application directly to the node where the data is residing. Additionally, we also have something called a multi-shard query coordinator, which I'm not showing in this picture, but for queries which span across all shards, the request goes to the query coordinator, which fans out, pushes those queries in parallel to all the shards. Each of the shard executes that query in parallel on subset of data it has, and then the results are returned back to the client application. So what are the benefits of sharding? Number one, it gives us linear scalability. That means that if we have more data, more transaction volume, then we add more shards and we get the same performance. There is no degradation in performance as we add more shards. So it basically gives us a straight line 45-degree scalability, which means adding shards online to increase the database size as well as the throughput. Additionally, this also gives us elasticity. I call it stateful elasticity. That means I can add more shards and rebalance the data or I can remove some of the shards without losing any data. So I can add shards or remove shards without losing data, and I can do all of this completely online. The second benefit of sharding is extreme availability. Here I'm talking about some of the applications where we are working with customers who need 4 nines, 5 9 SLAs. And this is about containment of an impact of a fault, or containing your blast radius of an outage. So in this architect example, if I have say 5 shards and shard number 2 went down, then it only impacts subset of data. If you are sharding by customers and your customer 101 to 200 were on say shard number 2, then only those customers will be impacted by this potential outage. Of course, as I said, there is no single point of failure in this architecture. There will be a failover, but even that small blip or brownout impacts a subset of user population. And that's what gives us the containment of an outage or the blast radius. The third big use case we see customers using sharding for is global databases, geographic distribution of data. Now, our customers are global, their applications are global, but with advent of a lot of new regulations in data privacy, data residency space, there are requirements where say United States data should stay within US. European data cannot leave the continent of Europe. We see customers having requirements in Asia Pacific where there are pretty much country specific requirements. The data cannot leave the geographical boundaries of a country or a continent for that matter. So with sharding, what we can do is we can have a single database which spans across multiple geographies. These databases, these shards could be deployed in multiple regions, and these regions could be in specific countries or continent. But from an application point of view or an operational point of view, it's a single logical database. The client's applications get connected automatically where the data is residing. But the data does not leave the geographic boundaries of the countries, and hence conforming to the data sovereignty requirements. So let's take a look at one of our biggest sharded database deployment. This is Oracle BlueKai. They are a part of our Fusion applications. This is deployed in Oracle Cloud, and this is probably one of the biggest online transaction processing database out there in the world. They have achieved transaction rates of 1 million transactions per second, and the total database size is 2.5 petabytes. They have 30 billion API calls per day. Each API call has a payload of 125 kilobytes, right? And with that payload and with that intensity of read and write, they are able to achieve the latencies of 1.6 millisecond for each API call for read, and the write latencies are 2.5 millisecond. And actually, in this application, every read is followed by a write. So every API call is a read followed by a write, which typically is called an upsert operations. So they're able to achieve such low latencies with such a big database size. Typically, when you see the database size grows, your latency increase. In this case, they've been fairly constant, and actually they are improving. The largest table has 22 billion rows. Because it's a write intensive application, they are generating 180 terabytes per hour of redo log. I mean, that's a pretty big rate if you think about it. All of this is running on 52 Oracle compute instances in Oracle Cloud. These are some of the big machines we make. The total number of CPUs across all these machines is 2,704 cores, and the total memory is 38,740 gigabytes. So these are big machines, and there are 52 of them, which are spread across multiple availability domains in Oracle Cloud and multi-regions. Now, each of these machines is backed up by a standbys, so I've only put the primary numbers here, but they have another 52 standbys which are being replicated too using Oracle Data Guard, and those standby machines and database instances are used for some other work read-only workload which is not included in these numbers. So these are like pure primary instances, and all of these API calls are being made against the primary instances. Now, you would think that that these latencies, as I said before, would be really hard to achieve with these size of databases. I doubt there is any other SQL or NoSQL product in the market which could achieve such latencies with this size of database. Another thing to note is that in this deployment there is no caching. All these numbers are directly coming from hitting the Oracle Sharded database instance. And this is our flagship relational database product, so they get all the good features around data consistency, transactions, asset properties, joins, etc. So that's an example of something which needs a really large scale. Additionally, Oracle Database is a converged database. That means we not only support online transaction processing and analytic workloads in the same database, but also different types of data. For example, you can store relational data, XML data, JSON, text, spatial, graph, all of this in the same database instance. And you can shard that database. So you can shard your relational data, which we just saw an example of. You can shard your text, you can shard your XML, you can shard JSON, you can shard graph, spatial, all of that. So what that enables us is to have a single sharded database for both structured and unstructured data. On the left of this, I'm showing how typically applications are built using multiple persistent store, different databases. And all of this is done for scale purposes. So you end up using a lot of different data stores, which are specialized data store for different types of data, and they are all sharded systems to be able to achieve scale. For example, if I look at a typical order processing system, you may have some Kafka, which is a sharded messaging infrastructure. You may have some order inventory, which is coming from a relational database. You could have some payment processing, which could again go to a relational because we are talking about dollars and cents, some payment gateway calls. You could have some shipping information, which you could be storing into a JSON format. Subsequently, order listing, which could be stored in text. All the product reviews, etc., could be text, right? So these different data stores require different specialized persistent store, which you need to procure separately. There is a different process to deploy them, install them, configure them, patch them, upgrade them, manage them, monitor them. They all have different set of APIs to be able to use them. And when you put an architecture like this together, sometimes when there is a problem, it's really hard to figure out where the actual problem is. Actually, we have real customer examples where the sites have been down for many days just because they couldn't figure out where the problem was. Everything seems to be working fine in isolation, but it was really hard to find the actual root cause. Additionally, if you want to run any queries across all of these different data types, it's literally not possible without writing some serious, without doing some serious programming. Which is, if I want to look at all my orders in last, say, 1 week, which sold over $10,000 and had a really good positive customer feedback, sentiment analysis on that, and we're in a specific zip code, then imagine writing a query which is spanning your relational database, your JSON store, your text store, your spatial and some of your messaging stored. With Oracle Database being a converged database, as we touched upon earlier, we can store all of these different data types in the same data platform. You could have separate instances of Oracle databases for, say, storing your relational, JSON, text, special transaction queues, and you can shard all of them, so you get the same scalability like many NoSQL products. Or you could even store all of these different types of data in the same database instance, in the same schema actually. And you can also run queries, a single query which can span your text data, relational data, JSON data. And of course, you can use sharding to get the scale which you're looking for. Some of the customer use cases, how customers are using Oracle Database Sharding. So this slide I put together by talking to some of our real customers who are, some of them are reference, others are not. And I asked them what other products did they actually consider before using Oracle Sharding. And then, so these are the name of the products which they covered. As I said, some of their case studies are available on our website, oracle.com. And basically, these are the reasons why they chose Oracle Sharding over these other products they considered. So an example are like internet scale online transaction processing applications. So things like mobile to mobile payments, point of sales, where you go to a gas station or a grocery store and you swipe your card and they look at what did you buy today and what is your purchase history, and they give you instant discounts or coupons. Credit card processing, etc. So a lot of those applications which need internet scale real-time transaction processing, where applications do need transactions, joins, basically asset properties, etc. So these customers looked at likes of Cassandra, MongoDB, MariaDB, Couchbase, Aerospike, ScalaDB, etc. And they chose Oracle because obviously they get all the great capabilities of relational database and scale of these like NoSQL products. Another category is global databases, which we touched upon. So where you have data sovereignty requirements, where US data needs to stay in US, European data needs to stay in Europe. We have customers doing that. Log stores or text data. Here you would think of things like Lucene, Solar, Elasticsearch like use cases. So this is your pure text use cases where you are doing things like search, Google like text search, sentiment analysis, fuzzy match, type ahead, all the regular text use cases, but at a large scale, at a large volume of data. So you can shard the text data and achieve the same set of use cases. Metric stores, time series stores, Internet of Things, things like infrastructure monitoring, application performance monitoring. So there are a set of applications used by our customers in that space where they have devices which are emitting data at a very high speed, deployed across these devices are spread across the globe, and the data is coming in, say, as JSON and getting stored and being analyzed in real time. Machine learning is another interesting use case, things like fraud detection. So some of our customers, for example, are looking at in the financial space as the fraud is happening. Say you swipe your credit card and the transaction gets scored for fraud, whether for example, your shipping address is different than your billing address. That might be something worth to look at. So applications like that, where machine learning is happening along with the data, where the data is sitting in the shard specifically. So pushing machine learning algorithms and logic inside the database and making it run right where the data is residing. Big data analytics. So I talked about the multi-shard queries or massively parallel processing. So in that space where you fan out your queries across multiple shards, scatter gather like pattern, map reduce like patterns, Spark, and other products in that area. So Gartner evaluated sharding as one of the criteria for ranking various databases. So this report is from 2019. They added a category for distributed variable data use case, and Oracle Sharding was ranked #1 in this space, and they called out some of the capabilities around hybrid clouds, distributed data, shards can reside on premise, on cloud, as well as the elasticity things I just touched upon. And you can see that Oracle Sharding was rated #1 here. I've put a link to the Gartner report as well. So sharding basically provides us best of the both world, which is provides us the extreme scalability and availability like many other NoSQL databases. Now, these NoSQL databases forced us to compromise on things like strict data consistency, full support for ACID transactions, two-phase commit, complex joins, trigger, store procedures. So we don't have to compromise any of that. With Oracle Database Sharding, we get the extreme scalability and availability of NoSQL, plus we get all the great capabilities of a traditional relational database. That includes Converged database. You can shard your relational data, text, spatial, graph. You can actually run a single query, as I said, across all these different data types. You can get all your strict data consistency, zero data loss. Get the full power of SQL and many other programmatic interfaces which you already are used to using. With sharding and the power of relational databases, the schema is maintained inside the database instead of application, because with a lot of NoSQL databases where the core database features are missing, a lot of that ends up happening is that we end up implementing logic in our applications to compensate for the lack of those features. So here we can leverage all the key capabilities in the database itself. And of course, Oracle Database supports all the enterprise grade features. All of these capabilities are available with Oracle Sharding. Things like in-memory, columnar, partitioning, sub-partitioning, compression, secondary indices, advanced security, backup recovery, storage management, data guard, golden gate, parallel queries, high performance storage engine, running the shards on rack, Exadata, all of that. So you can have all of that available with the Oracle Database Sharding. And of course, you already know how to provision an Oracle database and program against the Oracle database, so you can continue to use that. And often customers many times don't realize that they probably already own this sharding. It's included as a part of our database enterprise edition, so we don't need any additional licenses for that. And our customers, more often than not, they already have the license for this, and they know how to patch, provision, upgrade, monitor, manage an Oracle database, plus how to code against it. So it's already there, more likely than not. You already own it. So let's look at how it actually works under the cover. So in this picture, what I'm showing is something we call as a database, like a table family. So let's assume we have a database which has 3 tables: customer, order, and line item. We call this as a table family because they are correlated in some ways. So there are 3 customers, Mary, John, and Peter, and Mary has certain orders and line items, and so does John and Peter. What we do with sharding is that we take all of Mary's data, and let's assume we are sharding this data, which means we are partitioning this data, and there's the notion of sharding key. Let's assume customer ID is being used as a sharding key. So that's the key we'll use. So we take all of Mary's data and we put it on shard #1, which is in pink. We take all of John's data, which is in orange, and we put it on shard #2. And the gray shows Peter's data, so we take all of that and we put it on shard #3. The reason we do this is that when you run a join, we want to make sure that the join gets satisfied locally on a given shard, and we don't need to go to other shards to be able to satisfy that join. You can do that as well, in the sense that you can run joins across shards, but that is fully supported, but that does not give you the best performance. You get the best performance when you satisfy your joins locally on a given shard. So if I want to run a query which says, show me all the line items for Mary, that query goes to shard #1 and a join is satisfied and performed right here, and I get all the items which Mary bought so far. Additionally, we have a notion of something we call as a duplicate table. Now this data tends not to be that voluminous, so it's not needed, it's not required to shard it, but it is needed pretty much on all the nodes. A good example would be something like a product catalog. So it's not that voluminous, it does not change that often, and it is not specific to any customer, and it is used by all customers in this example. So what we do is we make a copy of that data, like a duplicate table we call it, or a reference data, and we make a copy of that data available on all shards. So now if I want to again run a join against a sharded table and a duplicate table, which is a reference table, my join again gets satisfied locally on a given shard. So if I want to see all the products bought by Mary, now again my query can be completely satisfied on shard number 1, and all the results will be returned back to the application. Under the hood there is a concept of chunks, and chunk is nothing but a logical construct. It is a group of related partitions for a given sharded table family. So in our example, we have this set of tables, table family for customer order and a line item. So let's assume there is a chunk number 1, and chunk number 1 has the information for or data for customer 1 to 1 million, their orders and line item. And that's what basically a chunk is. It's just a logical construct which just groups set of data for a set of sharding keys. And this is what a shard looks like. So in shard number 1, we have a set of chunks, and then we have the duplicate table data. So for example, chunk number 1 has information or the data for customer 1 to 1 million, their order and line items. Chunk number 120 has customers 5 million to 6 million, their order and line item. And then we have the data for the duplicate table, and that's basically what a shard is. And I'm using a relational database example here. Of course, this could apply to unstructured data as well. Same concepts apply there. Now, once we have partitioned the data, as I said before, from an application point of view, it's a single logical database. So all our drivers, whether it's a JDBC driver, C, C++, Python, Go drivers, .NET drivers, universal connection pool, they're all sharding aware. And they are also understand the data distribution and the partitioning at the back end in the database server. So they factor that into the routing of the request. Now, if I want to run a query and find out the orders or the line items for customer 1 to 3, my request gets routed to shard number 2 because we know that, say, the customer 1 to 100, customer ID 1 to 100 is on shard 1, 101 to 200 is on shard 2. So my request automatically gets routed to shard number 2, and hence the query is satisfied. As I said before, we also support multi-shard queries. So if I want to run a query which spans all the shards, for example, select count star from customer, show me all the customers I have worldwide, that query gets routed to the multi-shard query coordinator. This query coordinator component optimizes that query and then subsequently pushes that query to all shards in parallel. Each of the shard runs the same query on the subset of data it has in parallel, and the results are returned back to the multi-shard query coordinator, which gives it back to the client application. So in this case, if I ran a query select count star from customers and worldwide, then all my shards will be executing that query in parallel, and the results will go back to the client application. We also, so that's having a single logical database from an application point of view. Now, from an operational point of view also, this is a single logical database. We have something we call as a shard catalog. You can think of this as our administrative server. So you don't log into these shards or connect to these individual sharded databases. What you do is you go to the catalog and you do all your administrative operations from there. Things like adding shards, removing shards, moving data, creating tables, all of that. So if you have say hundreds or thousands of shards, you don't have to go into individual machines to be able to do that. You go to the centralized administrative server which does that. And this Catalog also acts as the multi-shard query coordinator, which we talked about, and also contains the gold schema and the master copy of the data for the duplicate table. So this is where we store all the duplicate table data, which is replicated onto all the shards, which is, so the catalog has the master copy, and then catalog also has the master copy of the schema, which is being deployed and created on all the shards. Additionally, there is a component called shard director, which you can think of as a database connection load balancer. So when the application connects, they don't specify the endpoints of the shards. They give the endpoints like the host port of the shard director. And then shard director knows what data is residing where, and if the topology changes where more shards are added or removed, or the data is moved across the shards, then the application is completely transparent to the application, because application does not connect directly to the shard. It only has the connect endpoint to the shard director component. So those are some of the components in the sharding and how the request flows. For high availability and disaster recovery purposes, each shard can be protected by standby. Say we can use data guard. So you can configure shards and you can define the number of replicas you want, and the configuration for your data guard, things like fast start failover, all of that, data guard broker, all of that is done automatically as a part of sharding configuration. So that's one way of doing for protection from local failure as well as from a disaster recovery point of view. Additionally, these replicas could also be configured to use active data guard, which means we can run all our read-only queries against the standby instances we have. We can also have each of the shard as a two-node rack cluster. These some of our biggest customers like China Telecom, which is a reference customer, big telecom provider in China. I believe they have over 300 million subscribers already, which is probably larger than the population of US. They have deployed in such a configuration. Another big bank in Europe, one of the biggest bank out there, they are using a similar configuration where each of the shard can actually be a two-node rack cluster. As I said before, these shards can be deployed as single instance databases in a shared nothing architecture, or if one wants, they can be deployed on a rack cluster as well. So some of the sharding methods, let's look at how do we partition the data and what controls we have on that. So we support 3 different sharding methods, and this is when I say sharding method, you can think about how how the data is placed on the shards. So first is system managed sharding. Here what we are saying is that I have a pool of machines and I want to spread my data uniformly across all these machines. I don't care which data element goes on which machine. In my previous example, if I have say 1000 customers and I have 10 shards, customer 1 to 100 goes on machine 1, 101 to 200 on machine 2, or whatever, in any order, or any customer can go to any shard. So what we do under the hood is we use a consistent hashing algorithm to spread the data uniformly across all of these shards. Now the advantage of this approach is that it's a system managed functionality. So as you add shards, remove shards, rebalancing of the data happens automatically. Though the downside is that you as a customer don't have explicit control over the data placement, right? So which customer ID goes on a specific shard, you just lose that control. The other sharding method we could use is user-defined sharding. So there are 2 options. One is by range and another is by list. So the range example is something which I used previously, where suppose I have 10 shards and I want to say customer 1 to 100 goes on shard number 100, 1 to 200 goes on shard number 2, 901 to 1000 goes on say shard number 10. So that's something I'm defining explicit range, and I have full control on what data element goes on which shard. But the downside is that as I add more shards or remove more shards, I have to worry about redefining my ranges and the data placement. Similarly, another mechanism in user-defined sharding is sharding by list. And here I can say something like, if the customer's state of residence in East Coast of United States, like New York or Florida, then put them into an East Coast data center like Ashburn, or if the customer's state of residence is on the West Coast like California or Oregon, then put them on a West Coast data center like in Phoenix. So I'm defining sharding and data placement based on a list of attributes. The third method is, we call it a composite sharding, and this is very unique to Oracle. There is no other vendor which I know of supports something like this, where what we are talking about is having two different sharding methods, each being used with a different sharding key. So what we can do is we can say first level of sharding is by range, second followed by a second level of sharding by consistent hash, or we can say list, first level of sharding is with list and then consistent hash. So it's two level of sharding and we are using two different keys. And this is what enables our global database use case. So for example, I could say that if a customer's country of residence is somewhere in North America, which is United States, Canada, Mexico, put them in a data center in US like Phoenix. Or customer's country of residence is somewhere in Europe like Germany, France, Belgium, put them in a data center in Frankfurt. And likewise for Asia, where if a customer's country of residence is somewhere in Asia, put them in a data center, say in Tokyo. And in Phoenix in US, I have 5 shards, so I don't want to deal with the micro management of the data placement across these 5 shards, so spread them uniformly across all 5 shards. So I use consistent hash. So one level of sharding is list based, which is the country of residence, and a key, sharding key there is the country where the customer resides. The second level of sharding is consistent hash, where I'm saying spread the data uniformly across all the shards available, say in Phoenix in US. And the key there is, say, customer ID. I could be using customer ID to spread the data uniformly. So two level of sharding, two different sharding keys, and that's exactly we call as composite sharding, and that's what enables our geographic data distribution use case. We also support something we call as a swim lanes, and this is an interesting pattern which came across by working with the different customers. And what the use case here is that we have partitioned our data, sharded our data in the data tier, and we want to use the same partitioning scheme for request routing of in our application tier and in our web tier. So the reason was that some of the customers we were working with, when they partitioned their data in the data tier, they were using things like memcached for caching in the mid tier. What was happening is that the data in the data tier is partitioned, so we have sharded that, but the mid-tier caches on all application server instances were having data from all shards. Obviously, instead of helping with performance, the mid-tier caches became a bottleneck. So what the customers did was that we provided them something called as a topology server, which is a REST API we can call to identify how the data is placed across the different shards. And with that configuration, the front-end routing tier, may it be a load balancer or an API gateway, routes a request for a given sharding key to only a specific web server, which talks to only a specific app server, which talks to a given shard. So the data partitioning which is done in the data tier has been extended to the mid-tier components, which is application tier and web tier components, and is being used for routing the request. Now with this application server only talks to this specific sharded database instance. It doesn't need to talk to other sharded database instance. That means this not only the cache footprint reduces, but also the connections for the database connections, this app server doesn't need to have connections to other shards. It just has connections to one shard. It also allows for things like A/B testing. So you could potentially roll out new changes to your data tier as well as to your app tier, whether it's deploying your new EAR or WAR files, which are applicable to only a subset of your customers. So I could roll out, say, new application changes to customer 1 to 100, and I just put all my changes only in one swim lane. And based on how my customers use the product and the feedback we get, we can subsequently roll out those changes to other swim lanes. And that's the concept of A/B testing. We support resharding and rebalancing of data. As I said earlier, this is sharding provides us a stateful elasticity. So that is to say that if I have, say, 3 shards and I added one more shard, and then I can rebalance my data across all shards. For example, I was having performance issues where all my machines were pegged, were fully utilized, and my data volume was still growing, so I could easily add a new shard and rebalance my data so that now I have, from 3 shards, I end up having 4 shards. So this is like, that was the before and this is after picture. Now all this resharding and rebalancing of data is a completely online operation. There is no downtime needed. Under the hood, we use RMAN incremental backup and transportable table spaces to replicate the data. And a chunk is the unit of data movement, which is what we talked about, chunk. So we move the data in the unit of chunks across these shards. We also allow for splitting of chunks. So for example, chunk number 1 had a customer ID 1, which has become very hot, whether in terms of number of queries or the data volume, and is causing a noisy neighbor problem. So what we can easily do is split a chunk and then move the splitted chunk to another shard. So all of that is supported completely online. Conversely, we can also shrink our size, the number of shards. So if I have 4 shards and I want to go to 3 shards, I can do that. And again, we can do online data migration completely online. And when all the shard data, all the chunks have been moved away out of shard number 4 in this case, then we can decommission that shard. So we support scale out as well as scale in completely online with sharding. You can use all the regular Oracle database tools. For example, for patching, you can use OPatch Auto, where all shards can be patched across the entire deployment. These tools understand the sharded database, they understand the catalog and how many shards are there. They support all of the things like rolling mode, standby patching first, etc. So that all is completely supported with sharding. For monitoring and management, those of you already using Enterprise Manager, you can continue to use that for sharding as well. We have enhanced the Enterprise Manager functionality for sharded database significantly in some of our more recent releases, where you can not only look at the data distribution, the number of shards you have, but also get to the specifics of the data for this specific key is in which shard, and within that shard this data is sitting in which chunk. It also gives you visibility into some of your hot shards where either the number of queries are running higher or the data volume is increasing, and these are the shards probably where we need to pay attention to to scale them out subsequently. So we have a lot of monitoring and metrics available around that aspect, where it gives you deep visibility into the data distribution into the sharded databases, as well as identifying the hotspots which might need an immediate attention. You can run sharded databases on Exadata. That's one of the best. It is the best platform to run Oracle Database, and all of the capabilities of sharding are supported on Exadata. You can use things like storage cell query offloading, ROCKY fast high-speed network connections, be able to use in-memory compression, all of that, columnar, all of that functionality which is available with Exadata is available with sharding on Exadata as well. And if you choose to use, you can configure each shard as a, say I was talking earlier, like a 2-node rack cluster, so you get an instant protection from a node outage as well. Let's look at some of the new features coming in 21C. Sharding has been around, was released in database version 12.2, and since then we have been adding features release after release. 21C was a big release for us, a lot of exciting new features, and we are working on many other features for some of the future releases, which I won't be able to talk about today. So one of the nice feature in 21C is with the universal connection pool for JDBC applications. We don't have to provide the sharding key. What we have done is enhanced our connection pool so that it automatically identifies the sharding key based on the bind variables for a given SQL statement. And what this helps us is that we don't have to make any application side code changes to be able to use sharding. So it also enables the automatic routing of queries. It knows that you're trying to do a single shard query, and if it can, it automatically figures that out and connects the application directly to the node where the data is sitting, or the shard to where the data is sitting. Or it can also do, in case of multi-shard queries, it automatically connects the application to the multi-shard query coordinator. So you don't have to worry about whether it's a single shard query or a multi-shard query or what's the sharding key, etc. So the work which typically an application side, or the changes to the application side, are obviated and not needed with this new functionality. We also have done some enhancements around deployment automation. So we released something we call as Sharding Advisor, and it's a tool by which you can analyze your existing database instances. If you're using Oracle databases and which are not sharded yet and you want to shard them, then you can run this tool and it gives you recommendations around how to shard your data. So it looks at the real usage like AWR reports. We look at a bunch of $V tables to see how the database is being used, and based on that, with the goal in mind to basically minimize the multi-shard queries where the queries are, where a single query needs data from multiple shards. So like push the queries onto a single shard as much as we can, in the sense that have the joins satisfied locally on the shard. So that's one of the goals, and maximize parallelism. So with those two goals, it gives us a set of recommendations where what should be the sharded table, which ones should be the duplicate table, and some ranking which would fit the sharding architecture nicely. Another set of automation we did were around deployment with Terraform, Kubernetes, Ansible. So you can deploy sharded databases on premises or in Oracle Cloud with these various scripting languages. We are also working on a Kubernetes operator for various operations in addition to just pure provisioning and deployment. So you can simply either edit a simple JSON-like file, define your topology, that these are my different shards, these are my primary, these are my standby, this is the machine I want to use for my catalog, this is the machine I want to use for my shard director, and that's it. And you run the script and it will go and provision everything and configure everything end to end. Or in Oracle Cloud, sharding is available as a part of the marketplace, where you just fill in a simple form, push a button, the automation kicks in and does the whole provisioning of your sharded database. We also added capabilities around centralized backup and recovery. So with this, what you can do is, as I'm showing on the right side, that with a single command, you can take a backup of all the shards in a sharded database. What we do is we force a SCN across all the shards, and then we take a backup for that SCN for all the shards. And what that gives us is a consistent backup across all the shards. Subsequently, we can do a restore. You can restore a given shard, or you could restore your entire sharded database. For example, if you have had an issue with the shard number 1, say 2 a.m. on Sunday morning, then you can just do a restore of that particular shard and leave the other shards as they were. Once you are restored, you can do a point-in-time recovery to bring it all the way to the time right before when the issue occurred. So you could just restore one shard. Or if you're running some kind of test harness where you take a gold image of all entire sharded database, you run your test cases which mutate the state, change the data in the system, and then for the next cycle you want to reset and go back to that gold image. So you can do again a restore for your entire sharded database, right? So we support both of them. These backup destinations could include, we're working on adding object store, ZDL array, etc. As the backup destination as well as we're working on providing chunk level restore for a given sharded database. This is another interesting feature which we introduced in 21C, and this helps with upgrade using shard replacement. Again, this came based on a request from some of our customers. So this helps with the upgrade as well as patching. So upgrade is like going from, say, 19C version of database to 21C. We call that a major version upgrade. Or patching is like when you're applying your patch sets, whether they are monthly patch sets like 19.6, 19.7, or security patches, one-off patches, critical patch updates. So all these database patches. So you can use this capability for all the patching as well as upgrade. And what we do here is that, let's assume we want to go from 19 to database version 19 to 21C. And we want to do it as an online operation, that is without taking any downtime. So what we can do is, in our given sharded database, we can add a new database instance, but it's an empty shard. So, but this is a version 21. So in sharding, we are allowing having different versions of database in a given sharded database instance. So here I can add an empty shard, which is 21C, and then I can move my chunks from my 19C shards to this newly added 21C shard. As I said before, moving chunks is an online operation, does not incur any downtime. So once I have moved all my chunks from my 19C shard to 21C, I can go and decommission my 19C database. So that way, this is a zero data loss, complete online operation, where I'm being able to upgrade, go do a major upgrade, major version upgrade from 19 to 21C. We also added functionality around persistent memory. Now, Intel has a chip called Opt-in, which allows to have persistent memory on the servers. And as the name suggests, this is a persistent memory, which means it's a non-volatile memory. The data in the memory is not lost due to things like power outage or when you reboot the machines. So what you can do is that you can have persistent memory on a given host, but you can only have so much persistent memory. For example, if you have a 6-socket box and each socket could have, say, 3 terabytes, then you can have up to, say, 18 terabytes of persistent memory. Out of that, let's assume usable is 15 terabyte. So I can have up to, say, 15 terabyte of persistent memory on each machine. Now, if I have a 60 terabyte database, I can't fit all of that into the persistent memory. And the idea is that that you can run your database, all the data sitting in persistent memory, and you don't need any other storage device like flash or SSD or SDD. So only storage on these machines is persistent memory. As I said before, persistent memory gives us performance similar to RAM, almost not quite the same, but fairly close to RAM. So what we can do is we can use sharding with this. So if you have 60 terabyte database, we can have 4 machines, each with 15 terabyte, and hence we can fit in a 60 terabyte database all in persistent memory. It basically becomes a persistent memory database. So we have enhanced our functionality like buffer cache, put a new file system, things to deal with things like fragmented writes, etc. So we have to make quite a bit of changes to Oracle Database to be able to support data sitting in persistent memory. But with that, all these changes are available in 21C, and we support this with sharding, where now you can have very big databases which are running entirely off persistent memory, and you effectively get the RAM like performance. Additionally, you can protect these database instances along with sharding and data guard. So if one of the node goes down and all your data is sitting in the persistent memory, you don't lose your entire data. The data guard will help us with a copy of this data, and the failover will happen to that node or to the standby. Now, with persistent memory, actually things like data guard failover also work faster, and that is because upon failover, what happens before the database is open for read-write is a lot of the pending change logs are applied, and they are read from the disk. In this case, because everything is in memory, all of that becomes a much faster operation, and the data guarded failover itself could be done in a much shorter time. Another capability which we added was a reactive stream ingestion library. So this is for some of the customers we are working with which have extremely high data ingest rate, and we were able to hit like almost 1 million ingest per records per second per node. So if you have 100 nodes, you can easily go to 100 million ingest per second. And the way we do that is by using something called as a direct path insert, where we bypass the entire SQL layer and we directly go to the block on which in which the data is would eventually belong, and we write the data directly into the block. So it's like bypassing a lot of layers, and hence it is increasing the performance. So with this functionality, we figure out which shard the data belongs to, and on that shard which block the data belongs to, and we go and write the data directly into the block. So that gives us an extreme performance number. As I said, 1 million ingest per second per node, and these are not like very big machines. These are just commodity hardware. So you can go to those kind of numbers, and we productize it and made it a part of our JDBC libraries, where now you can do streaming data. Reactive stream ingestion library is available with our universal connection pooling and JDBC capabilities. So in summary, sharding enables hyperscale globally distributed databases. We can use sharding with both structured and unstructured data. We can use sharding with online transaction processing as well as analytical workloads. It is included part of Database Enterprise Edition, and more likely than not, we already have it. So please go ahead and use it. Here are some of the resources. You can find more information about sharding, and here is my email ID if you want to reach out to me directly for any potential application which could benefit from sharding. Thank you very much for your time. Have a good day.